All right. If you remember, we were very concerned about the pH of the little pond where Becky and Billy do their fishing. The glass factory has a couple of different etching techniques because it gives them different looks on the glass that they use. They make art glass for installations in various places. In addition to the hydrofluoric acid, they also use a strong base. Several strong bases will do the same sort of thing for etching glass. This example that we're going to talk about is 15 molar ammonia, for instance, or ammonia solutions in order to use them to etch glass, which is, of course, they have issues with disposal of their waste, and maybe that's one of the things that's affecting the concentration of hydrogen ions in our pond. So, to understand how this bases might be affecting the pH, we need to think a little bit about how we can describe base equilibria. How can we take a substance that functions as a base and how does it react with water? How are we going to go through and do our equilibrium work with those things? Again, you have already got the core mechanic here. The fundamental piece of this puzzle is setting up an ice diagram and solving for the x's, the change values. That's the core mechanic for everything we're doing in this unit. What we're adding is a layer on top of that, that is, what if they give us a solution that has a weak base in it? How will we deal with setting up that equilibrium? How will we deal with the equilibrium constant? So the generic form of a base equilibrium constant, or a Kb, is a base reacting with water to produce the conjugate acid. This BH plus is the conjugate acid, and having it react with hydroxide, produce hydroxide ions. So remember, in our forward reaction, the B here represents some base, could be, say, ammonia. Okay, ammonia would be a good example. Ammonia reacts with water, just like this B reacts with water, and takes a hydrogen. So the base takes in a hydrogen ion. That's our Bronsted-Lowry definition of a base. The water molecule is actually functioning as our acid. It's giving off the hydrogen ion. So in the forward reaction, we have an acid and a base. In the reverse reaction, we have the conjugates, right? This BH plus, we call that the conjugate acid of base B. Okay? So this would be the ammonia, the ammonium to the ammonia, right? NH3, NH4 plus. And in the reverse reaction, this conjugate gives off the hydrogen to the hydroxide ion, which functions as the base to form the water molecule. Questions?
In the situation OH minus hydroxide would be a much stronger base than water.
Yes, typically the hydroxide would be a much stronger base than water. And if we think about the equilibrium of this situation, right, we're going to write out the Kb. For a weak base, this Kb, right, we leave the water out to liquid. For this Kb, this is typically weak. This value is much less than 1. So the reactants would be favored over the products.
For a conjugate base, conjugate acid is what came from
What came from a base, exactly. BH plus would be the conjugate acid. All right? So typical example is ammonia, right? Ammonia reacting with water, and that's basically just dissolving the ammonia in the water. This is what happens when we dissolve ammonia in water. It produces ammonium and some hydroxide. But again, the Kb value here is going to be less than 1. We're going to have to deal with this as an equilibrium situation. Strong bases typically work a little bit differently. So if we imagine our 15 molar situation here, the Kb for the ammonia is 1.8 times 10 to the negative 5. You know how to do this. You can set up the ice diagram. We're going to end up with the x values, which are going to be our change, and then our equilibrium values for the ammonium and the hydroxide. And we're going to have 15 minus x. Again, we make our 5% rule assumption, and you have x squared over 15. You get your x value of 1.6. This is not new. All this work right here is stuff we've been doing for the last 3 weeks. Okay? The new bit is just this stuff right here. When we talk about a base dissolving in water or a base equilibrium constant, Kb value, it's the base reacting with water to produce its conjugate acid and hydroxide. That's the reaction that we're describing with a Kb value. Okay? Just like our Ka value was an acid breaking apart into hydrogen ions and its conjugate base. So, this X value is the concentration of the hydroxide ions, as well as the concentration of the, in this case, ammonium, the conjugate acid. So if we take the negative log of this number, that's going to give us the POH. POH. So if I wanted to find out the pH of this solution, what would I need to do? I'm going to do the 14 minus POH to get the pH. In this case, that would be 12.2. Yes, if we're in an aqueous solution, the water autoionizing Kw is going to absolutely hold true. That's where this comes from. This equation right here with the 14 minus, that comes from Kw. That comes from the fact that we're in an aqueous solution and the water equilibrium is still true.
Why do you know it's POH, not like PNH?
Well, because we have the hydroxide being produced here. That's where we got the POH from. Because we took the negative log of the hydroxide concentration. P just means take the negative log of whatever this is.
Wouldn't it be the same as PNH? Because
Yeah, if we don't take the PNH4, we could do that. But typically in these problems, yes, it would be the exact same value. Typically in these problems, we're interested in the pH because that's how we describe the overall concentration or acidity of the whole solution.
where do you get the 14?
The 14, remember the root of this equation right here is Kw equals hydrogen ions times hydroxide ions. So the Kw is 1.0 times 10 to the negative 14 at room temperature, 25 degrees Celsius. And that's why we get the 14 from. Negative log of that value gives us 14. Questions? No? Okay. So, same basic equilibrium. The new bit that you got to keep in mind is when I give you a Kb value or something like that, you need to think, oh yeah, I see this reaction in my head, the base reacting with water to produce its conjugate and hydroxides. That's the important thing here. It's a direct analog to what we did yesterday with the Ka values, where we had the acid breaking apart. This is the base reaction, the base dissolving into water, the base reacting with the water.
Is it always going to be, there's always going to be an excessive
Say it again?
There's always going to be OH.
For a Kb value? Yeah. The way that we write these always have the hydroxide in it. If you see a Kb. That's the way it's described. All right. So, in addition to direct bases, right, the sort of ammonium, sodium hydroxide, the bases that we're familiar with, there are other things that could be influencing it because the glass factory is actually being kind of careful. They're taking their effluent, they're taking the stuff left over from their work, and they're trying to neutralize it. So they have the hydrofluoric acid reaction, right, that they're using to etch. Well, they neutralize that hydrofluoric acid with sodium hydroxide. They're not trying to pollute the environment. They're trying to keep their the pH coming out of their factory balanced. So they take their excess hydrofluoric acid and they add some sodium hydroxide to it. So the sodium hydroxide and the excess hydrofluoric acid react and they neutralize each other. Okay, and we've seen these kind of neutralization reactions before, right? We have sodium hydroxide reacting with hydrofluoric acid, and that's going to produce water and sodium fluoride. The key thing that they're having some trouble with, that they're not possibly taking into account, is the fact that this sodium fluoride, the sodium and the fluoride are essentially conjugates of acids and bases. So they are conjugate acids and bases themselves and may, in fact, have acid-base properties that we need to be aware of. So what we need to think about is how do salts, and salts, remember, in this context of chemistry is another word for ionic compounds. What are the acid and base compound properties of these kinds of salts? Okay? If I have sodium fluoride, what are the two ions that are, when I dissolve sodium fluoride in water, what two ions do I get? I get sodium ions, and I get fluoride ions, right? Na plus and F minus. This stuff doesn't really form in water. They don't stick together in water. We know that from essentially our simple solubility rules. And we're going to talk a lot more about solubility because it's actually an equilibrium problem that we're going to have to solve in a couple of days. So, what we want to think about is well, how does the sodium ion behave in water? Could this sodium ion function as a base? Could the sodium ions react with water to produce hydrogen ions? Okay, for this reaction to take place, what would have to be formed and stick together in the water? Sodium hydroxide. For this reaction to happen, sodium hydroxide has to stick together in water. If the sodium hydroxide doesn't stick together, then this reaction doesn't take place. In other words, the equilibrium constant would be really, really small value. So small as to be close to zero. Okay? And so what we need to think about is, hey, what do we know about sodium hydroxide? What kind of base is that? It's a strong base. What does a strong base mean? Totally breaks apart. So does this reaction take place? Nope. This reaction does not happen, and we know that because sodium hydroxide does not form in water. They do not stick together. They completely split apart. Conjugates of strong acids or strong bases do not have acid-base properties because strong acids and strong bases are not equilibrium situations. They run to completion. They completely break apart. These things don't do anything. Now, the conjugate of a weak acid, for instance, this fluoride ion, this fluoride ion, if I have it dissolved in water, for instance, if I took solid sodium fluoride and dissolved it into water, we know that the sodium ion is not going to do anything. It can't react with the water. That doesn't happen. But what about HF? Does hydrofluoric acid stick together in water? Yeah, its Ka value is pretty small. So I know that the hydrofluoric acid will actually stick together in water. So that the fluoride ions can pull hydrogens off of the water molecules. This reaction can take place. And it will take place. It's an equilibrium, yes. But what I need to think about is how much does this take place? How much hydroxide ions will be produced if I put fluoride ions into the water? What I need is the Kb value for this fluoride ion. Because this is what we were just talking about. This is a base reacting with water to produce hydroxide. This is a Kb. This is a base reacting with water. If I had the Kb for this reaction, I could do calculations, I could find the X values, I could do all that fun stuff that you already know how to do. Here's the trick. When you're talking about a conjugate, you can calculate the Kb value for this one, or a Ka value if you're dealing with a weak acid, from Kw. It turns out that Kw is going to be equal to the Ka value for an acid times the Kb value for its conjugate. Okay? So in this case, the Kb value for this conjugate base, and that's what fluoride is. This fluoride ion is the conjugate base of our HF. I can calculate its Kb value from its Ka and Kw. And the Ka value would be given to you, for instance, or we could look it up for homework in our textbook, or it's in the lecture notes that I've given you. Was it 1.7 times 10 to the negative 4, or 2.7 times 10 to the negative 4? If you look at the notes from yesterday, it's on there. So, you can see we have Ka times Kb would equal Kw. We can use that to solve for Kb or Ka. And it's not just any Ka and Kb. They have to be conjugates. They have to be related to each other, like that F minus is related to the HF. They have to be conjugates of each other. Okay? So, what we're saying is, even after we neutralize, even after we have that reaction of sodium hydroxide and hydrofluoric acid, and if we add exactly equal molar amounts, which you might do in a neutralization, you're going to end up with these fluoride ions in the water, and those fluoride ions are going to cause the solution to be basic. And so unless the glass factory is being very careful about how they do this, if they're just neutralizing in a very simple way, they could be producing salts, ionic compounds, that are changing the pH of the water. Questions? Yeah. You're in a line, so it's hard.
If like the
Eliza.
Na reacted with the water, like
If it could.
what it would be more acidic.
Right.
And that would be
The conjugates of weak bases function as acids, and conjugates of weak acids function as bases. Because the conjugate is always the opposite part, right?
they both.
If we won't do that to you, because if you have a weak acid and a weak base, if this was say NH3 or this is NH4, then you have two equilibriums happening at the same time that are interrelated, and you end up with multiple equations, multiple unknowns, and it gets really complicated to solve mathematically. So generally, what we're going to see in this class is going to be the conjugate of something strong with the conjugate of something weak. So we only have to deal with one equilibrium at a time. And so that's where we're going to sort of draw the line. If you go on and take more advanced chemistry in college, you might have to deal with situations because we're really isolating individual pieces of what's happening in the water. Lots of stuff is happening at the same time. And there are ways we can simplify it by saying, oh, well, that one's so small we don't have to worry about it. But in the case of conjugates of weak, both of them are going to be happening and both are going to influence each other in a significant way. And you would really need to solve the equations simultaneously to get a realistic answer. If they're both strong, the conjugates don't do anything. And then we just do stoichiometry and we're done. And tomorrow we're going to talk about how all these mixing things happen. When I react this with this, what is the result? So that's tomorrow. That's what we call titration. We tell it within a simple way. We have to add equilibrium to make it more accurate.
So the Ka, well, I'm just confused, like, so the Ka value to get that from the Ka of Na or the
Right.
Ka
So
of
typically, if you go and look up values, you're not going to find a Kv value for fluoride ions because people don't list them. Okay? What you would find is you would find the Ka value for the weak acid HF. And you would find, for instance, if you had ammonia NH3, you could find the Kb value for that. We typically look up Ka and Kb values for the neutral compound. And then we calculate the converse. So you can look up this Ka value, and then they would expect you to calculate the Kb for the ion, the conjugate of whatever the neutral compound was. You look up the Ka for HF. HF is the acid. NaF is a ionic salt. It doesn't have a Ka or Kb value by itself. It's just an ionic compound. Because by itself, it's not an acid or a base. It's only once the ions form that they can react with water and do this. Okay? So, we have these equations, right? We have this sodium fluoride. We know the sodium's not going to do anything. It's this fluoride reaction that's the important one. Fluoride ions react with water to produce hydrofluoric acid and hydroxide ions. Okay? So, what we are getting out of the glass factory is a 0.3 molar sodium fluoride solution. So their effluent, their waste, is 0.3 molar sodium fluoride. Okay? The Ka value for hydrofluoric acid is 7.2 times 10 to the negative fourth. What is the pH of the solution? What is the pH of this solution? You're going to need an ice diagram, but before we draw the ice diagram, what's our very first thing we got to do? We need a balanced chemical equation, the one I just showed you. Okay? So, and the key thing you got to think about, is it the NaF that reacts? What does the Na do? Nothing. It's the conjugate of a strong base. It's unimportant. It does not react. It's the fluoride ion that's the important bit. Okay? When the problems give you a salt, an ionic compound, and talk about acid-base stuff, you have to think about the two ions that are in there and figure out which one actually does something. Base your reaction off the one you think is going to do something, the conjugate of the weak acid or base. Yes, the concentration of the fluoride ions would be 0.3 because for every one sodium fluoride, how many fluorides do I get? One. 1-to-1 ratio. So 0.3 sodium fluorides gives me 0.3 fluoride ions and 0.3 sodiums. But the sodiums we don't care about, they don't do anything. We don't even need to worry about them in the ice diagram. They don't do anything. Because remember, sodium fluoride solution, the sodium and the fluoride completely split apart. They're highly soluble. They're going to completely separate into ions. It doesn't matter. The volume of the solution doesn't matter. Because it's all based on molarities. As long as the molarity is the same, it doesn't matter what volume you have.
Should we assume the 5% rule?
Yes, you can assume the 5% rule. That's close enough. All right, so do this. You've got the box. 0.3 molar sodium fluoride. Remember, the fluoride's the important part. Does the water show up in your equilibrium? It's a liquid. It's a liquid, so it doesn't show up in your equilibrium calculation. All right? Do this problem. All right, so let's take a look at this. We'll walk through it step by step. You have this chemical equation. I know everybody's got to this point. So we need to set up our ice diagram, right? Our initial concentration of fluoride, where does the fluoride come from? Sodium fluoride. Remember, the sodium fluoride dissolves in water, splits apart to sodium ions, which we said don't do anything, and the fluoride ions, which react with the water to produce hydrofluoric acid and hydroxide. So we can set up our ice diagram, 0.3, 0, 0. We know we have to shift to the right. We can't shift to the left because we don't have any products yet. So we're going to use up some of the fluoride ions to make hydrofluoric acid and hydroxide. Why do I leave this water column blank? It's a liquid. It's not part of our equilibrium calculations. Okay, pure liquids or liquids and solids we leave out. So I have 0.3 minus x and x. Now, what do I need to set that equal to? What kind of equation is this? Is this an acid reaction? Nope. This is a base reaction, so I need a Kb value. So I'm going to find my Kb value from the Ka and the Kw. My Kb is going to be 1.4 times 10 to the negative 11. Does this Kw value change? For our purposes, no. In real life, if you change the temperature, it changes a little bit. But on the useful equation sheet, they give you this Kw value. They give you this equation. Ka times Kb equals Kw equals 1.0 times 10 negative 14 at 25 degrees Celsius. It's on the useful equation sheet. So we know Kb, we're going to set that equal to the mass action expression. Remember that? So 1.4 times 10 negative 11 equals x times x over 0.3 minus x. Let's assume that this x value is small so that we can simplify this equation. 1.4 times 10 to the negative 11 equals x squared over 0.3. X equals 2.0 times 10 to the negative 6. You will always be able to use the 5% rule on our test and on the AP test. So what does this value equal? That is our concentration of hydroxide ions. So that's our concentration of hydroxide. But this problem asks me to find the pH. So there are two ways to go here. One, we can take Kw times, or Kw equals concentration of hydrogen ions times concentration of hydroxide. So the hydrogen ion concentration would be Kw divided by concentration of hydroxides. And then once we get that, do the negative log. Or we can take the negative log of this number to solve for the POH, okay, to get us the POH. And once we have that POH, we're going to do the 14 minus to get the pH, 8.3. Yes. That's why I'm teaching it to you. Take the negative log of this number. So on my calculator, I hit the negative button, I hit the log button, I type in this number, I hit enter, and it'll spit out this number. Okay? So again, this core equilibrium mechanic, set up the ice diagram, plug in the values, solve for x. This is all stuff we've been working on. Treat it as a tool. Guys, treat that as a tool to solve equilibrium problems. Your key is recognizing what is the equilibrium I'm dealing with. That's the new bit. Instead of having just gases reacting or something, we now have very specific structures to the equations. We have this is a base equation. That gives us a Kb. We have acid equations with Kas. We have water reacting. That's our Kws. Okay? And we're going to see some more KSPs for solubility products. Okay? So we need to identify what type of equilibrium we're using and to help us know what equilibrium constant should I use in this equation. But once you've got that, this is just the same ice diagram mechanic we've been doing. We use the 5% rule to simplify, we solve. Then we got to do a little bit more thinking around, well, we have hydroxide concentration. They want pH. How can I get there? Okay? And I'm using this, which is a K based on Kw, in order to do that change. Okay? All right. So we've started to identify some of the issues with the pond. We need to start to think about how can we control that pH. How can we take control and keep it where we want it? How can we deal with neutralizing the stuff that's there and establishing some sort of buffer in order to maintain the pH where we want it? And that's what we'll talk about tomorrow. Alrighty, righty?
Yep.
Excellent. You do have some homework to do. We need to practice. This is more equilibrium practice.